Welcome back to Physics for the MCAT. Today we're going to be covering Chapter 5, which is Electrostatics and Magnetism. Chapter 5.1 covers charges. You probably already know all of these things, but we're going to go over them really quickly anyway. So charges come from subatomic particles. The proton has a charge of +1, and an electron has a charge of -1. So attraction and repulsion in the context of charges means that opposite charges attract each other and the same charge will repulse each other. So two electrons will have two negative charges and they will repulse each other. So when we say that a proton and electron have 1 unit of charge each, we mean that they have 1.6 times 10 to the -19 coulombs of charge. And this constant is sometimes denoted by the letter E. So in order to ground a charge, this means to return the charge to Earth or to return it to something neutral. This is why if you have static electricity on you, then if you touch a doorknob, this will send the charge back to the door frame, which will send it back to the ground. Conservation of charge means that, like mass, charges can never be created or destroyed. They can only be neutralized, which means that when a positive and negative charge are together, they will be neutralized, but you will always have the same amount of positive charges and negative charges. Insulators are materials that don't distribute charge well over their surface, and therefore they can't transfer a charge well. So if you put a charge on the surface of an insulator, it'll stay where you put it, and therefore it won't transfer it to any other materials. Insulators are typically non-metals. Conductors, on the other hand, distribute charge very well on their surface, and so they can transfer charge to the next object very efficiently, and conductors are usually metals. Chapter 5.2 covers Coulombs Law, and Coulombs Law is the equation you'll use when you want to calculate the electrostatic force between two charges. So this is an example of why I think units are really helpful. So Coulombs Law, in order to solve for the electrostatic force, the equation is K, which is a constant, times the charge of the first charge and multiplied by the charge of the second charge, divided by radius squared. So this constant K will almost always be given to you, and it'll be given to you with the unit. So if you can't remember this equation, you can just look at the units. So we know that the unit for force is a newton. And so if we want to solve for the force, which is in newtons, and we have some form of equation multiplied by this constant, we know that this equation must cancel out the meters and the charge. And therefore we know that on the bottom we should have radius squared, and on the top we should have the two charges. And that is exactly the equation. And so even if you can't remember this equation, when you see the constant, you'll know exactly what to do to find the force. Chapter 5.2 also covers the concept of an electric field. So an electric field is basically the concept of, well, what would happen if there was only one charge? Like, what would be the strength of this one charge's repulsion or attraction on other charges? And so you can envision an electric field like this in the picture to the right. So you have a big Q, which is the source charge, and then you have a little q charge. This is called a test charge. So this test charge is only hypothetical. All we care about is what the big Q is doing. So how we can find the magnitude of an electric field, which is denoted by E, and it's in units of newtons over coulombs, is that we can take the electrostatic force and we can divide it by the test charge. So what we're saying is that this electrostatic force would be the interaction between these two charges. But now, because we're looking for the magnitude of the electric field, we don't actually care about the other charge anymore, so we're just going to divide it out. And so in other words, this is K multiplied by big Q, which is the source charge, divided by R squared. And you can see this really easily from the units of E. E is newtons over coulomb, so it's just the force divided by one of the charges. So we just divide it out because we don't really care about the test charge anymore. And so this test charge, little q, by convention is positive, which means that this E describes what would happen to a positive test charge if it was in the electric field of the source charge. And so if instead your test charge was negative, you would just take whatever vector you would find from E, and you would turn it the other way because it's negative. Other than solving for the strength of the electric field, we can also draw field lines around the source charge. So in this picture, we have two hypothetical source charges. One is positive and the other is negative. And so around these, we can draw field lines, which represent the direction that the test charge would move in if it was placed in this electric field. So remember that by convention, the test charge Q is positive. And so if we had a positive source charge, these field lines would go outward because the charge would be repulsed. And if the source charge was negative, we would draw the field lines inward to represent the hypothetical movement. And also note that the field is strongest where the lines are closer together. So we can see here that the field is strongest around the charge, and the field gets less strong far away from the charge. And this is also important because electric field lines are vectors, and therefore the charge would be accelerating faster if it was closer to the charge, and it would be accelerating slower if it was further away from the source charge. And this makes sense because if you're closer to a repulsive force, you will get repulsed more and accelerate more. And so here I have a question, which is when placed 1 meter apart, which would experience a greater acceleration, 1 coulomb of electrons or 1 coulomb of protons. So we can remember that each electron and each proton have the same amount of charge. And so 1 coulomb of electrons would be the same amount of electrons as 1 coulomb of protons. However, they have different masses. So when we remember our equation F equals ma, we know that these two electrons and protons will exert the same force on each other from our equation with Coulombs Law. Because mass isn't connected to Coulombs Law, however, the masses are different. So electrons have a much lower mass and protons have a much higher mass. So if we know that the forces are equivalent and electrons have lower mass, electrons must have higher acceleration. And because protons have a higher mass, they must have a lower acceleration. So the answer here is that the electrons would experience greater acceleration because the force is the same, but they have less mass. Chapter 5.3 covers electric potential energy, and electric potential energy is given by this equation here, which is in units of newtons times meters, which is the same thing as a joule, which makes sense because all energy is given in the unit of joules. What this unit also tells you is exactly what the equation is, because a newton is the unit of a force, and if we think back to the equation for electric force, it was kq over r squared, and if we take that times meters, that's a measure of radius, and so we can cancel this out, and this gives exactly that equation. So if you don't remember this equation, just remember that electric potential energy has to be in units of energy, which is newtons times meters, and that just gives you the equation right there. Electric potential energy can also be thought of as the amount of work required to move a charge from infinity to where it is. So if you think about it, if we have two positive charges next to each other, if you let's say this one is stationary, this one is the source charge, which is always stationary, and you let this charge go, it'll just go and be repulsed out to infinity. And so the potential energy of this charge is the work required to bring it from infinity back to where it is. And all that these equations are saying is what I was saying before, that this is the equation for work, and cosine theta in this case is 1, because you will just be following the field line exactly at 0 degrees. And so the equation for work reduces to force times distance, which is the same thing as electric force times radius, which just gives you back this equation for electric potential energy. So the electric potential energy is the amount of work you need in order to move a charge from infinity back to where it is. Chapter 5.4 discusses electric potential, which sounds very similar to electric potential energy, except for one small difference. So when you note in the equation for electric potential energy that you need both a source charge as well as a test charge. But what if you wanted to know the potential of the field without the test charge, just the field itself? So then you would use the equation for electric potential, and this is in units of volts or joules per coulomb. And like we learned before, if we want to remove the influence of the test charge, we simply divide it out. So we just take the electric potential energy divided by the source charge, and this gives you this equation here. And you can also know what this equation is by thinking about the units, joules over coulombs. So you take the equation that gives you joules and you divide it by something that gives you coulombs. And so this tells you the energy per unit charge, which is important because you could put any charge of test charge in there that you want, and it'll give you varying amounts of electric potential energy. So electric potential, it's important that this is in volts because this is connected to the concept of voltage. Voltage is the potential difference between any 2 points. So if you have a charge Q that moves from point A to point B, the voltage would be delta V. So this would be the electric potential at point B minus the electric potential at point A. So you might see this equation in the book, which is work over the test charge. This is the same thing as the equation for electric potential. However, work is used to denote that something is being moved. Chapter 5.5 is about special cases in electrostatics, and the first are equipotential lines, which are basically just lines on an electric field that have the exact same potential. So if we look at this picture that we've seen before, we can draw equipotential lines, for example, here. So that circle is supposed to be centered, but basically every single point on that circle has the same potential, which makes sense because they should be the same distance from the source charge. And so if we look at where the test charge is, we can similarly draw, that's a terrible circle, we can similarly draw an equipotential line here, which means that no matter if the source charge is where it is, or if it's over here, or if it's over here, it would have the same potential. The other special case is an electric dipole. An electric dipole is when a positive and negative charge are separated by a really small distance, and the positive and negative charge have to be equal in magnitude. So when we have an electric dipole, as shown in the picture over here, we can calculate the potential from it just by subtracting one from the other. And so we can use the equations that we had in the slides before, where we have V1 minus V2, and this is because charge number 1 is positive and charge number 2 is negative. If they were both positive, we would just add both of them, but that wouldn't be a dipole anymore. So we would take charge 1 minus charge 2, and so this would give KQ over R1 minus KQ over R2, where K is our constant. Q is the charge, in this case it's -1, and here is R1 and here is R2. And so it basically gives us this result. And so if we can assume that D is very, very small, and in comparison the distance R's are very, very big, then we can approximate it to this equation here, where D is the distance between the two parts of the dipole, and R squared is this are these distances. And because R is really big, we assume compared to D, we don't distinguish the difference between R2 and R1. We just use the average here. The cosine theta term here is important because it matters what angle we're measuring from. So in the picture, we're measuring from this angle here, but let's say instead we measure from this angle here. This is exactly 90 degrees to the plane of the dipole. The plane of the dipole is here. So if we were exactly 90 degrees, this gives us a cosine theta of 0, which makes sense because if we are at this 90 degree angle, we're equally distant from the negative Q and the positive Q. And so this gives us no difference between the two. And so R2 minus R1 would be 0, so this entire term would be 0, and thus this would also be 0. This also makes sense on a conceptual point, because if both of these were the same distance, then the field from both of them would just cancel each other out at 90 degrees. And that's why the angle is important. I should have mentioned that none of this dipole moment stuff is particularly important for the MCAT, but it's in the book, so I wanted to cover it. And you can represent the dipole moment as a vector, P with a vector arrow over it, and P is also equal to the charge Q. So as we mentioned, the positive and negative sides of the dipole moment must be the same charge. So this Q is the magnitude of that charge, and then the D with a vector on it is just the separation distance between the two parts of the dipole. And so one of the things that a dipole can do is a dipole can rotate in an electric field. So when we have any kind of rotational force, we represent it with torque. And torque is P, which is the magnitude of this dipole moment vector. So it's just the magnitude of it without the direction. E is the electric field strength that we found in a couple of slides ago. And then sine theta is the angle between this plane and the electric field. So if you were ever asked to calculate the torque of a dipole, this is how you would do it, but I really don't think any of this you will be asked to do. Chapter 5.6 is about magnetism, and here we talk about a magnetic field, which is created by any kind of moving charge. So we explained before that an electric field is what causes charges to move, and a magnetic field is what is created when charges do move. And so the unit for magnetism is in units of Teslas, which is this unit here. But because 1 Tesla is very big, it is often more convenient to use the units of Gauss, which is 10 to the negative 4 Teslas. And you've probably heard all of this before, but a diamagnetic molecule or diamagnetic substance is one that has no unpaired electrons, and therefore it doesn't have a magnetic field, it doesn't have a dipole, and therefore it doesn't really interact with magnetic fields. A paramagnetic substance does have unpaired electrons, and it interacts weakly with magnetic fields. Ferromagnetic is, some people consider it a type of paramagnetism, some people consider it a completely different type of magnetism, but basically it's just anything that interacts very strongly with a magnetic field. So some examples of these: diamagnetic includes like all hydrocarbons and most organic compounds, because all of their electrons are paired. So that's why, like, if you have a tree, it doesn't respond to a magnet. Paramagnetic substances are things like oxygen, gold, like things that respond very weakly to a magnetic field. And ferromagnetism, as the name suggests, iron is your classic example of something that is ferromagnetic and therefore reacts really strongly to a magnetic field, because iron has a lot of unpaired electrons. So to find the magnitude of this magnetic field that's caused by moving charges, we can use this equation here for any linear wire filled with moving charges. So we always represent the strength of a magnetic field using the letter B, which is why a magnetic field is often called a B field. And so for a linear wire, we have the equation B equals U naught, which is called the permeability of free space, or the permissivity of free space. Either way, it's just a constant. Multiplied by I, which is the current of the wire. You'll probably be given this value, or you'll be asked to calculate it with different equations that will be mentioned in the next chapter. R is the distance you are from the wire, and divided by 2 pi r. And so this is where the right-hand rule comes into play. So let's say we have a wire that is going up in this direction, and you wanted to know the direction of the magnetic field. So you would take your right hand, you would point your thumb in the direction that the current in the wire is going in, and then the way that your fingers curl is the way that the magnetic field would go around your wire. And so why this is important is, let's say that you are here, right? And so this is your R, which is the distance that you'll plug into the equation. Then if you were here, according to the right-hand rule, your magnetic field would cause a force coming out of the plane. However, if you were here, this would have the same R, so your magnitude of the B field would be the same. However, your direction would be different. You would be now pushed to the right by the magnetic field. So always remember the right-hand rule when finding the direction that the magnetic field is going in. The equation is slightly different for a loop of wire. So like if instead of having just a linear wire going one way, you had a circular loop, with current going in a circle, then you would have this other equation. It's the same as the one above, just without the pi. To figure out which way the magnetic field is going in a loop, we can also use our right-hand rule. So if we look at the right side of this loop and we take our thumb and we point it up this way and we kind of curl our fingers around it, we can see that our fingers are going into the page on the outside of the loop, and our fingers are coming out of the page on the inside of the loop. This might take some imagining, but basically the current is going, or the magnetic field, because the current is going in a circle counterclockwise, the magnetic field is rotating around this way, in the same way that your fingers are curling. So you can see that this magnetic field is going into the page on the outside of the loop, and it's going out of the page on the inside of the loop. This is the notation we use. We use dots to mean coming out of the page and X's to mean going into the page. And if we repeat the same exercise, if you try to hold your right hand on this other side, we can see that on all the sides, on the outside of the loop, your magnetic field is coming into the page, and on the inside of the loop, the field is coming out of the page. Great, so now we know the magnitude of our magnetic field, and we also know the direction that it's going in. But what's important about magnetic fields is what they do to other charges that are moving near them. And so let's say we have a charged particle that's here, moving this way with velocity v. The velocity will be given to you, and we can call this charge Q. And we also know that at this point where the charge is, the magnetic field is moving in this direction with magnitude B. And so remember that the magnetic field is not constant. The magnetic field is different at every point. So like in this example, you could have a wire going this way, in which if we use the right hand rule, and we point our thumb in the right direction, we know that this is going into the page over here, and it's coming out of the page on this side. If you just pretend to grab the arrow with your hand, you can see what I mean. And so this magnetic field is moving in a circle. Sorry, I'm not very good at drawing. This magnetic field is moving in a circle, kind of into the page and out of the page like that. And so at this point B, we could be somewhere like here, where the direction is perfectly into the page. Anyway, so we already know that we have a charge moving at velocity v to the right, and our B field is going to the front. And so then we can use this equation where the force on this moving charge is equal to Q times V times B times sine theta. And this equation is pretty easy to remember because you basically just multiply together everything you know. And then to find the direction of this force, sine theta, the theta is between the direction of the B field and the direction of velocity. And so here we can see that it's 90 degrees. So when it's 90 degrees, that's when the force is greatest, because that's when sine is equal to 1. And so we use this other version of the right-hand rule where you point your thumb in the direction of the velocity, you point your fingers toward the direction of the magnetic field, and then your palm is the direction of the force. So I like to imagine this as I stick my thumb in the direction of velocity, I stick my fingers in the direction where the magnetic field is pushing it to go, and then I use my palm to slap the particle. So you that's the direction the force is applied, the direction that you slap the particle in. And the equation is similar for the force in a wire. So instead of having a singular particle V moving this way, if instead we had a whole entire wire, and all of the charges on the wire are moving in this direction with velocity V, and so we would take the current of the wire multiplied by the length of the wire multiplied by the strength of the B field. And this makes sense because the current of the wire times the length of the wire is kind of like the charge times the velocity. The current is like kind of the velocity, and the length of the wire is kind of the amount of charge that you have, multiplied by the strength of the magnetic field multiplied by sine theta, which is once again the direction that the charges are moving in times the direction of the B field. This is theta. And so you can kind of imagine using the right-hand rule again, and you're kind of slapping the wire into the upward direction. And that concludes chapter 5. Thank you so much for watching.